Let's take a look at advanced production analytics and optimization, a solution that combines MindSphere and Technomatic's plant simulation. It helps you to identify bottlenecks and improve throughput based on real load cases. In the following demo, you will hear about a typical connected shop floor scenario for food and beverage. The storyline is about a soda producer that has different lines consisting of the same machines. It starts with a PET blowing process to produce the bottles. After the leak testing step, the bottles are filled with soda and capped afterwards. A pick-and-place robot puts the bottles on the trays. The company has the line connected to MindSphere to monitor different variables and performance of the stations. In addition, they also have a plant simulation model available, which they used initially to design and plan the line. In this storyline, the plant manager checks his filling line reporting dashboard from time to time to make sure that everything is performing as expected. Therefore, he opens up Operations Insight, a MindSphere standard application with data visualization, dashboarding, and KPI calculation capabilities. He opens up the relevant dashboard, and there he can see that the throughput on his filling line is going down over time and is currently not at an acceptable level of 78%. This needs to be resolved soon. He calls up the industrial engineer to investigate the current behavior. The industrial engineer picks up the task and opens up the MindSphere closed-loop discrete events simulation application. She has already set up a relevant study in the application, which maps the physical variables with the simulation model input parameters. In the Runs tab, she selects the relevant time frame and triggers the simulation run. The simulation package is now sent to the plant simulation environment, where it can be used for production replay and bottleneck analysis. The industrial engineer opens the MindSphere interface in Technomatic's plant simulation. She loads the digital twin template by establishing an authenticated connection to MindSphere. The MindSphere interface loads the simulation runs, and the engineer selects the desired simulation package. In this step, the operational data is applied to the simulation model. The industrial engineer performs the production replay by running simulation using the event controller. The application now shows the plant running virtually as if it would in reality. The user then opens the bottleneck analyzer tool while also running the production replay. On clicking the Analyze button, each machine resource utilization can be seen. The machine, which is experiencing the most blockage, errors, and waiting line, can now be identified. This tool helps the user visually identify the bottlenecks in the plant. In this case, it is the leak testing machine. Once the production replay is complete, simulation results can also be uploaded and visualized in MindSphere. After the industrial engineer identified the leak testing machine as the bottleneck, the maintenance engineer starts to investigate on the leak testing machine and has a first look at the events on this machine. He sees many warnings regarding a low air pressure on the compressor and wants to follow that path. He compares this leak testing machine versus a leak testing machine of a parallel line to see if there are bigger differences in the compressor behavior. The maintenance engineer sees that the compressor loses its pressure entirely, stops for some time, and then slowly builds up the pressure again until it loses it again. The compressor on the parallel line can keep the pressure up as expected. Before making a decision whether to buy a new motor for the compressor or repair it, the industrial engineer must verify how the plant will operate when the leak testing machine is fixed. A study can be created which maps the data of all the machines except the leak testing machine. This study can be used for what-if analysis. The user verifies the threshold limit for the blocked state. She then selects the study specifically created to perform what-if analysis and create a simulation package. The user then loads the simulation package design for what-if analysis. She then modifies the simulation model to change the leak testing machine's operational characteristics. In this case, the operational rate is defined to be 75%. It is changed to 99% based on the new motor's performance rating. The simulation run results are uploaded in MindSphere. Another what-if analysis is performed to see if the newly fitted motor allows higher resource utilization of the leak testing machine. Parameters are changed, and the operational data is applied to the model. The results are then uploaded to MindSphere, where you can compare and contrast the simulation results for the two scenarios. The MindSphere UI can be used to quickly check resource statistics under different conditions to find out the best possible model configuration. What-if analysis can help the customer make a sound decision that is backed by simulation data. In this case, the results show that replacing the motor improves the performance and solves the problem. After the motor has been replaced by the maintenance engineer, the plant manager checks again his dashboard and can confirm that the throughput of the machine goes up to an acceptable level again.